Hello. Yes, hello and welcome to this class on probability. And I'm your teacher. My name is Avijit Sarkar. Oh, this doesn't write too well. Let me get another marker. Now, can you all hear me loud and clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
All right. So that's who I am. And the topic for today would be probability. And I just wanted to find out from you all that do you have this book? ML Agarwal, ISC Mathematics?
Yes, sir.
Okay, that's good. Because I would be using this book as a basis for this class, and I would frequently be assigning you problems to look at, problems to review, theory to review out of this book. So it's important that you get this book. Now, a few of you may belong to like CBSE board, but honestly, like, there isn't much divergence between the syllabuses of CBSE versus ISC. And it's a really nice book. A lot of examples have been worked out. So I would suggest that you get this book if you don't have it already yet. But from what I gather, everyone does have that book. Okay. So
No, sir.
let's get
I have the
started.
book
Yes.
Sir, I don't have the book presently for the class, but I'll make sure I have it for the next classes on.
That will be nice because see, I mean, you can, so I'm presuming, who am I speaking to? What's your name, please?
So Yashvi Singh.
Yashni?
Yashvi, sir, yes.
Okay, okay. So I presume you are under the CBSE board. So you have a
Yes.
different, okay.
Yes.
Well, actually, this book does have its advantages in the sense that, like a lot of problems have been worked out, and I personally feel it's an invaluable resource simply from the standpoint of having all these like problems, like that have been solved. So having all these problems at your disposal. So it's an invaluable, like, book to learn out of. So I would suggest, get this book and work your way through the examples. It's a good reference to use. Okay. So let's get started. So I presume that everyone has had some probability in class 11, correct?
Yes,
Hello?
sir.
Yes, okay. So what I'm going to do today would be, so it must have been a while ago that you looked at probability theory. So I'm going to just start out this class, we are going to go nice and slow and easy. I'm going to start out this class by reviewing what you had, like seen in class 11. And one of the challenges of this topic is that it's a little abstract in the sense that we all intuitively understand what probabilities are. Like probability of an event is simply the fraction of times you expect the event to happen. When a trial is conducted a large number of times. You take a coin, you keep on tossing it, maybe you toss it 1,000 times, then we all know that the probability of getting a head, the fraction of times you're going to get a head would be about half. So you're going to get about 500 heads if you toss a coin 1,000 times. So we all intuitively understand what probability is. And, like even before we get introduced to the theory formally, which I think happens when you are in class 10. But then if you notice that what we had done is use the language of set theory to describe probability, where events are described as subsets of this set called sample space. So it's all a little, like abstract, but there's a good reason behind it. Okay, so let me start with the reason. And then after that, what I would like to do is, like not spend too much time, but like spend some time explaining to you how how the language of sets, like facilitates the description of, themes in the theory of probability. So I'm going to start out by saying a few things about calculus. Like you all have had calculus, I presume. So long before, as you know, like calculus was discovered or developed by Newton. and also by this mathematician by the name of Leibniz. And then there were others, even Newton's teacher in Cambridge, Isaac Barrow, he developed a great deal of calculus. The fundamental theorem of calculus that you have come across is generally attributed to Isaac Barrow. So this development in calculus really started, around the 1500s, 1600s, and it really took off. A lot of theory was developed in a very short span of time. However, if we trace the roots of calculus, even 2000 years ago, Archimedes, the mathematician, the Greek mathematician that you may have heard of, I'm sure you've heard of, Archimedes. Even Archimedes, what he managed to do was, he managed to compute the area under some simple curves. Let me get another marker. This doesn't write too distinctly either. This is a good one. So when you study definite integrals, you learn how to compute the area under a curve. Okay, so let's say this is y equals x squared. You learned how to construct these rectangles, right, over a given interval a to b, how to construct these intervals, and then through the limiting process, you took the width of each interval to go to 0, and that gave you the area. Now this technique was known by Archimedes as well. He used what's known as the method of exhaustion, okay, and it's a fascinating method. So using that method, it's absolutely similar to what you had seen in the context of definite integrals. So using that method, he was able to, derive the area under some simple curves like y equals x squared, y equals x cubed. And what he did was essentially the same as what you saw. He divided the area under these simple curves over a given interval into lots of little rectangles. He reasoned that when the width of the rectangle goes to 0, what the area should be, and he was able to derive the area under some simple curves. He was able to derive the formula for the area of a circle, the formula for the area for the volume of cones, of spheres and pyramids, and so on and so forth, using his method of exhaustion. Okay, so calculus actually, in a sense, began with Archimedes. And also the Indian mathematician Aryabhatta, he is known to have calculated instantaneous rates of change. He was studying the orbits of the moon as it went from the earth. And it is known that, he concerned himself with calculating instantaneous rates of change, which falls under differential calculus. Now, the reason why these two mathematicians, Aryabhatta and Archimedes, in spite of the power of their methods, they were not able to really develop the theory of calculus in a way that Newton and Leibniz was able to do. And the reason was they lacked what may be termed as the language of limits. The whole idea of limits, it wasn't known during Archimedes' time and Aryabhatta's time. In an intuitive sort of way, they anticipated this idea of limits, and they were able to do some calculations based on that. But the theory of calculus didn't quite develop till the language of limits was introduced in calculus. And what this language did was provide calculus on a very sound, theoretical basis. And against this framework, the subject of calculus, the theory of calculus, it found support in this framework and was able to develop. And the development of calculus really took off, at a fast pace ever since the language of limits was introduced to calculus. Likewise, probability theory. When we introduce the language of sets into probability theory, what it essentially did was it made all these intuitive notions that we had about probability, we were able to firmly tie all these intuitive notions into a solid framework, and the framework was strong enough that it allowed for the development of probability theory. So there are things that we intuitively know about probability theory that can be described very efficiently using the language of sets. And using the language of sets, we were able to do theoretical work and stumble upon results in probability theory that were not really intuitive, difficult results. So that's why the language of sets has been introduced into probability, just to give you an idea. Okay. So any questions so far? I just wanted to mention that I really encourage the asking of questions in my class. So always feel free to like pause me and ask me a question if you have one. Okay. So what I'm going to do next is take a bit of time to talk about this, this abstract language of probability theory using the language of sets. Now, before that, one thing that you should know is what lies at the heart of probability theory is what's known as a random experiment. Okay, and just let's take an example. Let's try to understand this with an example. So let's say I toss a coin twice, just once. So what are my outcomes? I can either get a head or a tail. Now I can list these outcomes efficiently as follows. Okay, I get either a H or a T. And let's say I roll a dice. Then these are my 6 outcomes. Okay. Now, before I toss a coin, I know very well what the possible outcomes are. It's either a head or a tail, but I do not know before tossing a coin. I do not know whether the coin is going to come up heads or tails. Likewise, for a dice, I know very well what the outcomes are. The grand set of outcomes. I know them. But before I roll a dice, I do not know what outcome I'm going to get, right? So such experiments or trials, if you will, or tests are referred to as random experiments. And they're characterized by the fact that for a random experiment, we know very well what the outcomes are, but we cannot predict ahead of time what outcome we are going to get. So that's random experiment. And this idea lies at the heart of probability theory. Okay. Now, the other interesting thing that I wanted to point out to you about random experiments is that in almost all situations, okay, it is natural to assume that these outcomes are equally likely to happen, right? So when we toss a coin, we know that it's equally likely to come up heads or tails. When we roll a dice, we know that the dice is equally likely to show one of these 6 numbers. Okay. So in a situation like this, so basically based on this observation, we can conclude that if we toss a coin over and over again a number of times, then what would happen is in the long run, we would expect, and when I say in the long run, I mean after a lot of trials, 1,000 trials, 1,000,000 trials, we would expect that half the times the coin is going to show up heads and about half the times the coin is going to show up tails. Okay. So this actually paves the path for the intuitive definition of probability, which I mentioned at the beginning of this lecture, namely that the probability of an event is the fraction of times we expect the event to happen. Okay. So if we were to put some numbers around this, so let's say n is the number of times we toss a coin. Okay. And now let's take this fraction and let's imagine n is really large, and we can impose that restriction that n is really large. We can be more precise about it. Let's say limit as n goes to infinity, and let's observe this fraction whose denominator is n, representing the total number of trials, and whose numerator is number of times a head is observed. Okay. So it is reasonable to conclude that this ratio, as limit n goes to infinity, is half. Right? Now this, what you have on the left hand side, is the intuitive definition of probability. Okay, this is the definition, you know, like this is the intuitive understanding of probability that we all grow up with. Now here's the amazing thing. I mentioned at the beginning that the description of probability using the language of sets, okay, it lends that this theory a very strong framework based on which we are able to prove, you know, a lot of interesting facts about probability, and we can also develop the theory beyond what our intuition would have normally permitted us to. And one of the amazing things that we can prove using the axioms of probability, which I'm sure you read about in class 11, but we are going to briefly touch upon it in today's lecture as well. So based on these axioms, it is actually possible to prove that this is indeed the case. Okay, that the probability of an event, you know, like is essentially when you conduct a random experiment over and over again, you know, the frequency of times that this event occurs, this event in question occurs, the frequency of time, it tends to converge to a specific value, which happens to be half in the case of a coin tossing experiment, when the event in question is that the event that a head occurs. Okay, so that's one of the crowning glories of axiomatic probability theory. And when I say axiomatic probability theory, I mean, you know, like this language of sets and the axioms that go with it, along with the proofs that go with it. Okay, so it's one of the crowning glories, and it's in fact called the, you know, like the strong law of large numbers. It's not an easy proof, it's not an easy theorem, but just so you know, like, I mean, some of you might be wondering out there, like, why do we, you know, like take a concept such as probability that is so easy to understand, you know, like when we flip a coin, obviously we expect the head to occur 50% of the times and tail to occur 50% of the times, or in other words, half the times, heads and tails. So why do we make it so complicated by introducing set theoretic language? And I myself actually, like, you know, when I was your age, I used to, you know, I was a little baffled at this formal theory, you know, like that was used to develop probability theory. Then, and much later, I realized that it actually enables us to prove a lot of things that we intuitively know to be true for probability. Okay, and as a matter of fact, next class, I don't think we're going to get there in today's class, we'll be studying a phenomenon in probability, again plays a central role in probability. It's what's known as the phenomenon of independence, independent events. And even there we'll see, we are going to first start out by talking about, you know, I'm going to try and like instill in you a certain intuition about independence, and then we'll see that how nicely the theory actually tends to validate what we intuitively would understand about independence. Okay. Okay, so having said that, let's just briefly get into, you know, the nuts and bolts of the theory. Okay. Any questions so far?
No, sir.
I'm sorry? No questions. Is that
No,
what?
sir.
Okay. Give me just a second. I wish to keep track of time. So we are going to go 15 minutes overboard, if that's okay. I'm sorry, I came in a little late, so we'll make up for it. So hopefully everyone can stay on for an extra 15 minutes. Okay. So when it comes to formalizing probability theory, and I'm not going to spend too much time on this because you all already know this. We just talked about outcomes of an experiment. outcomes of tossing a coin, outcomes of rolling a dice. Okay, so you ought to know what sample space is. I'm pretty sure you already know that. Sample space is nothing but a systematic listing of all the outcomes of a random experiment. Okay, so I had already, like, before I erased this board, I'd already written down the sample space for tossing a coin once, which happens to be h comma t, a set containing h and t, and the sample space for rolling a dice, which happens to be a set consisting of the first 6 positive integers. So sample space is simply a list of outcomes, possible outcomes of a random experiment. Okay, so the next thing that you need to know is what's an event. Now again, intuitively we all understand what an event is, but now what we are going to do is we are going to attempt to define what we intuitively know to be events in the language of set theory. Okay, so let's take an example. Let's say our random experiment consists of tossing a coin twice. Okay, so in this case, sample space, which is usually denoted as S, okay, what would the sample space look like? It would look like this. The coin, the first flip could be a head, in which case the second flip could be a tail or a head. The first flip, when I say flip, I mean toss. The first flip may result in a tail, in which case the second outcome, the second flip may result in a head or a tail. So that's my sample space. Okay. Now let's take 2 events. So first, before getting into the set theory part of it, let's try to describe these events using plain language. Okay. So let A be the event. By the way, is this visible to everyone, what I'm writing down?
Yes, sir.
Yes.
Okay, good. So let A be the event. That a head occurs on the first toss. Okay. And let B be the event that a head occurs on the second toss. Okay. So now if we are to list the outcomes that correspond to A and the outcomes that correspond to B, what are we going to get? So A is the event that a head occurs on the first toss. So the first toss would result in a H, meaning that the second toss would result in a H or a T. So that's A for us. And how about B? B is the event that a head occurs on the second toss. So the second toss is a H, meaning the first can be a H or a T. So that's B. So now notice that A and B, under this framework of set theory language, A and B are both subsets of S. They're both subsets of a sample space. So in that sense, events are described to be subsets of a sample space. Okay. So this is the thing to note, that these are both subsets of S. Okay. So now using any questions so far? Okay.
No, sir.
So yeah, so this is just something that you need to get a little used to, like thinking of events as subsets of a sample space and so on and so forth. Now what we are going to do next is we are going to use A and B, and I want your focus to be here for now, not here, okay, which is the abstract definitions of A and B. So this is A and B described in plain language. Okay. So now consider the event that A and B occurs. So imagine, so the event is described as A and B. So, and let's assume it occurs. Okay. So then what can we say about the outcome? So they both occur simultaneously. That's the whole idea. So if A occurs, that means we have a head on the first toss. If B occurs, we have a head on the second toss. So if both occur, that would mean that we would have heads on both toss, correct? So intuitively we know that if A and B occurs, then there would be a single outcome for this event, HH, right? Now notice, now let's shift our focus to the set theoretic definition of A and B. Notice that if I take the intersection of these two sets, and like commonly, as you know, from set theory, and when you have and separating two sets, you need to take the intersection of them. So if you take the intersection of A and B, then what do you get? You get precisely this. So this is an example where the language of set theory, okay, it is describing for us very effectively what our intuition tells us about what A and B ought to be. Our intuition tells us, based on the the definition of A and B using plain language, our intuition tells us that A and B should correspond to the outcome HH. And notice that the language of set theory, like when we take the intersection of these two events A and B, it precisely defines for us what A and B means. Okay. Now let's take another example. So I'm going to erase this part. Oh, actually, a large part of the board is visible to you, so I could have left that. Anyway, so now let's talk about the event A or B. Okay, now here's something for you to bear in mind. In mathematics, the word or is used in a very special sense. So in everyday language, if I say that I want to have tea or coffee, okay, I mean that I would have either tea or coffee, but not both. But in mathematics, whenever you have the word or showing up, and this is something I'm pretty sure you have seen in the context of set theory. Okay, so when we say A or B, okay, and in this case, A and B are events. So let's say we say that A or B occurs, this event occurs. We mean that A occurs or B occurs or both occurs. Okay, so that possibility of both A and B occurring is actually included within this or, which is why or in mathematics is often referred to as what's called a inclusive or. So in other words, it includes the possibility that like both events occur. So now again, what we are going to do is a little exercise whereby we are going to first ignore this set theoretic definition of A and B. We are going to just focus on A and B as they are described by plain everyday language, okay, and ask ourselves, what would this event look like? What would the outcomes corresponding to this event be? Okay, so if A or B occurs, that means we have a head on the first toss, or a head on the second toss, or head on both tosses, right? So how many ways can that happen? Okay, so let's look at the sample space. So if A or B occurs, we'll have a head in the first toss, which would correspond to these two, or we'll have a head on the second toss, or we'll have a head showing up in both tosses, which would be this, right? So our common sense of logic tells us that the outcomes corresponding to A or B should be HT, HH, or TH. Okay. And now, if we now shift our focus from this definition of A and B using plain language onto this definition, notice that if we take the intersection of A and B, oh sorry, I meant the union. If we take the union of A and B, because the word or, as you already must have seen in set theory, the word or corresponds to taking unions. what are we going to get? Okay, we'll get exactly this set, right? So this again demonstrates that just like you know, an event such as A and B, you know, just as that can be effectively described in terms of intersection, the event A or B can be effectively described in terms of a union. Okay, a union of the two events when these events are considered to be subsets of a sample space. Okay, so any questions so far? And
So, like the meaning of or in mathematics, could you define it again?
yes, yeah. So, you know, the word or, so let's forget probability for a second and get into set theory. Okay. So let's say there's a set A and a set B. Okay. And suppose there's an element X, and suppose we say that X belongs to A or X belongs to B. Okay. So what this means is that X either belongs to A, or it belongs to B, or it belongs to both A and B. Or in other words, so that's just a definition. That's just a convention that we use in mathematics, that when we say or, okay, so again, let me repeat myself. X belongs to A or X belongs to B means three possibilities. Either X belongs to A, or X belongs to B, or X belongs to both A and B, meaning X belongs to the intersection. Okay, so that's what it means. So this actually translates into saying that X belongs to A union B. Okay, now in everyday language, when we say that, you know, something, you know, like X belongs to A or X belongs to B, we mean that it belongs to A or it belongs to B, but it cannot belong to both in everyday language. Like you know, like I mentioned, like, you know, if I say that, you know, I want tea or coffee, I would like to have tea or coffee. We mean that, I mean that I would have either tea or coffee, but not both. So in mathematics, you know, if a mathematician says, I want to have tea or coffee, the mathematician means that, you know, that he would have either tea or coffee or both. Okay. So that is why, you know, this is just a terminology, inclusive, you know, or is used in an inclusive sense, meaning that when we use or, you know, like between two conditions, okay, condition 1 or condition 2, okay, so we mean that either condition 1 is fulfilled or condition 2 is fulfilled or both are fulfilled. Okay, is that clear?
Yes, sir.
Okay, and I just wanted to ask the class, am I going too fast?
No, sir, it's okay.
Am I going too slow?
No, sir, it's
Not
okay.
too slow.
So I mean, like, you know, because see, basically before I came into for today's class, I was thinking that it must have been a while that you looked at probability theory, probably a year ago, right? Correct me if I'm wrong, but I'm guessing it must have been
Yes.
like a year
Yes, a year ago.
in class 11. So, you know, that is why, you know, I was thinking that I made up my mind to like kind of, you know, review all the basics. So I hope that's not a waste of time for you, you know, and you know, you should like feel free to tell me that, no, you know, we really know this stuff. So you
Actually,
can
I
like,
had doubts on the basics only. So
fantastic, because you know what, the basics are really hard to master. But I'll tell you one thing. To master this, all you need to do is spend some time with it. You know, it's not so much of understanding it. It's more like getting used to it. Okay, and I'm really tempted to tell you, and you know, admittedly I'll fly off in a bit of a tangent, but what I'm going to present to you is a very useful tool for learning mathematics. Okay, so many of you, or I'm presuming at least some of you, may have heard about the great mathematician John von Neumann. Have you heard of von Neumann? Anyone?
no, sir.
Okay, so you feel free to look him up in Wikipedia. You know, he's generally considered to be one of the giants of 20th century mathematics. So very recently, just some time back, about a month ago, I came across a quote of von Neumann, which actually helped me understand the basic nature of mathematics, some parts of it at least, and how learning mathematics should be conducted as a student. See, I mean, even I'm a student of mathematics. I'm learning new things, like every day, at least I strive to. So what von Neumann said is that there are parts of mathematics in which there isn't much to understand. It's about getting used to it. And I thought about it. When I came across the statement, it seemed a little, like provocative. Maybe not entirely true. Maybe it was just a provocative statement. So, he was saying that there's not much to understand. In fact, he said, no, there's nothing to understand. Nothing to understand. You just have to get used to it. And then when I thought about it, this is what I came up with. Let's say this is the set of everything that we understand. Okay? So this, I'm calling it a set collection of everything, all the ideas and concepts that I understand. And let's say a new concept gets introduced to me. What does understanding that new concept mean? What it means is that you will try to understand this new concept in terms of things that you already know. You would somehow try to fit this into the framework of things that you already know. And when you can fit it into that framework, you would say, okay, I've understood it. However, this new concept may be such a novel concept that maybe you don't have the framework to accommodate it. You don't have the framework to understand it. So at that point, the best thing to do would be what von Neumann said. Get used to it. And once you get used to it, what that would do is, it would in fact expand your existing framework. That's what it would do. So really, like when you encounter a new topic in math, one of two things can happen. Remember this. Either you'll be able to understand it in terms of what you have already learned before, or it would be such an alien idea that you won't be able to understand it in terms of what you know before. Another example would be permutation combination. Remember, I think most of you will agree. It was a very different kind of mathematics. And without going into the nitty-gritty details of what makes it different, I think we all agree, that it was very new. So when you have a really novel idea, a very new concept that's different from everything that you have seen before, when that gets introduced to you, just get used to it. Okay, just go over it over and over again, these basics, revise them, the definitions. And then, like one fine day, you will get the feeling that, yeah, like I really understand it. So what's happened is your existing framework has expanded owing to this new idea. But using your existing framework, you may not be able to understand it. Okay. So hope I made sense. Did I make sense?
Yes,
what I said?
Yes.
Okay. All right. So remember that. So that applies for probability theory. And I'm really glad that I'm, like brushing up on this old ideas. Okay, so what have we seen before? What are we trying to do here? What we are trying to do here is we all intuitively understand what probability of an event is. So what we are trying to do is trying to put a mathematical framework around it. Okay, we are trying to organize what we know about probability in terms of a mathematical framework, and this mathematical framework is the language of sets. We are borrowing that language to describe probability and events and phenomenon related to probability, and we'll see plenty more of those in this course. So we are trying to describe phenomenon related to probability using the language of sets. So that is something you already know the language of sets. So you need to just get used to the idea of thinking about a sample space as the set of all outcomes of a random experiment. Everything starts with a random experiment, mind you. And that's something you should be, like very clear about. And then you have to get used to the idea that an event, what's an event? It's a subset of a sample space. Okay. Now, sometimes events can be described very nicely and very precisely. Event that a head occurs on the first toss, but it doesn't need to be. Even this is an event. Okay. Although that can be verbally described, even that we have two tails, or a tail on either toss. But you may have events, like which you may not be able to precisely and nicely define, but it doesn't matter. Okay. And also remember, each element of the sample space is also an event, like this one, the event that two tails occur. Okay. Each element is an event. Okay. Because each element considered as a set can be thought of as being a subset of the sample space. So in fact, such events are called elementary events, and we'll have chance to get into that at the end of this lecture. So to continue, so the next thing that we noticed was that given two events A and B, I'm just recapping what we just did. Given two events A and B, okay, the event A and B occurring can be very effectively described in terms of intersection of the events A and B when you consider A and B to be subsets of the sample space. Likewise, given this verbal, description of A and B using language, plain everyday language, we can talk about what it means for event A or B to occur. Okay, and then we noticed that A union B, in fact, very effectively describes for us, okay, what A or B means, okay, in plain everyday language. So far so good. I suppose it's clear.
Yes, sir.
Okay, all right. So let's move on. So now let's talk about so just as we can talk about an event A occurring, we can also talk about the event A does not occur. Okay. So that's the third event that we are taking up. The first one was A and B occurs, A or B occurs, okay, and A does not occur. Now, if A does not occur, again, ignore this. Ignore the set theory description of A and B. Let's focus on plain everyday, description of A and B using language. So A is the event that a head occurs on the first toss. So when we say that A does not occur, it means we don't get a head on the first toss, correct? So what do we get on the first toss? We get a tail, okay? So A does not occur. What would the outcomes look like? We'll get a tail on the first trial, meaning on the second toss, we'll get a H, or we'll get two T's, okay? Now notice something interesting. Now what we are going to do is shift our focus to the set theoretic definition of A and B. By the way, I'm using this term quite frequently. Set theoretic. If set theory is a noun, set theoretic is the adjective. So set theoretic means pertaining to set theory. Okay. So I just to clarify, because you have come across the word set theory, but you may be wondering what I mean by set theoretic. It's just the adjective of the noun set theory. So A does not occur. We saw intuitively, just based on the description of A, it would mean that these two outcomes are the only possible outcomes. Now, let's look at A as described set theoretically. Okay, A is HH and HT. Now, think about the complement of A. And what does the complement of A mean? Complement of A comprises of all those elements that are not contained in A. Correct? So you have come across complements in set theory. And in the book, they have used all kinds of notations for complement. There is this notation, and then there is this notation. Okay, so just pick and choose a notation that you are comfortable with. I am comfortable denoting complements by putting a C at the top. So I would be doing that. And obviously you are expected to make your own notes where you should use the, the notation that you are most comfortable with. But you must be familiar with all those notations, because you never know in the exam what notation they would be using. Okay. So I take it everyone understands what complement is. So now if we look at the set theoretic description of A, and if we take the complement of it, what do we get? Okay, so A has HH and HT in it. Okay, so it has HH and HT in it. So the complement of A in the sample space S, that's a universal set, would be TH-TT, and they are the same. So the event A does not occur is precisely modeled by the complement of A, precisely modeled as in precisely described by the complement of A. Okay. So that should tell you, like, the power of this language of set theory. So what we are being able to do is translate everyday usage of, like language to describe, events, and we are translating them into their set theoretic analogs. Okay. Any question on that?
No, sir.
Okay. All right. Now for there's let's see what's the next item on my list. So now we are going to talk about two types of events. Okay. And the first type would be, and this refers to not just one event, but a collection of events. A collection of events under certain circumstances is referred to as exhaustive events. So what does exhaustive events mean? Exhaustive events, so let's write down that term. Okay. So these are events. So first let's take an example. Suppose A is, as we have described it, event that a head occurs on the first toss. And let's think of another event, C. Let's call it C, but I'm not going to write it down. I really don't need to. So A means first toss is a head. C means first toss is a tail. Okay, let's imagine C means first toss is a tail. Now, if you think about the event A or B, the event A or B translates into saying that the first toss is a head or a tail. So what can you say about A or B? What can you say about A union B? It will be the entire sample space, because all these outcomes should either start with a H or they should start with a T. Okay. So what these two events A and C, what they effectively achieve is, if you take the union of them, you get the entire sample space. Okay. I didn't write down C, but I hope that was clear to everyone. Okay. So exhaustive event means that if A, a subset of S, and what does this mean? A is an event. That's what it means. If A, a subset of S, and B, a subset of S, has the property that A union B is all of S, then A and B are called exhaustive events. So they exhaust the sample space. Okay, when you consider the event that A or B occurs, okay, it covers the set of all possible outcomes. So that's what an exhaustive event is. Any questions on this?
So means exhaustive events basically means the all the possible outcomes.
Exactly. See, to understand this abstract language, always keep an example at the back of your head, which is why, I'm presenting this lecture the way I am. For corresponding to each abstract definition, you must have an example behind your head. So the perfect example for exhaustive events is, now see, this A and B have nothing to do with this two A and B, because, they don't exhaust the sample space. If you take the union of them, you'll be missing TT. Okay, so remember that. So example of exhaustive event would be, let's say one event is that we get a head on the first toss. The second event is we get a tail on the first toss. Now, no matter what outcome we are talking about, it should always start with a head or a tail. Okay. So if A and C are defined to be events such that A means we get a head on the first toss and C means we get a tail on the first toss, A union C would be the set of all outcomes. So when that happens, we say that A and B are exhaustive events. Okay, is that better now?
Yes, sir.
Okay, good. And like I said, the moral of the story is always keep some examples at the back of your head. And like I said, in von Neumann style, you need to, based on his advice, you need to get used to this whole idea. And the best way of getting used to a new abstract idea is examples. Okay, examples are critically important. Now, this idea of exhaustive events can be expanded. How so? It doesn't have to be two sets. Two events don't need to exhaust the set, the sample space. There can be several events. So an extension of this idea is that if A1, A2, AN are events, by the way, so this is just, saying that these are events. Okay, so you need to start thinking of events as subsets of sample space. So if these are events, meaning they are all subsets of sample space, with the property that A1 union A2 union, so the union of all of them is equal to S, then we would say that this collection of events A1, A2, AN are exhaustive. So the word exhaustive, always applies to a collection of events.
So means in the example which you have given above, there A union B, that event is exhaustive.
That is not exhaustive. That is not. Okay. So A union B is not exhaustive. As I mentioned, the last definition that I wrote down, okay, A and B featured in the definition, but as standalone items, they had nothing to do with this A and this B. Because if you look at A union B, okay, forget about this. Look at A and B as described here. Okay, head occurs on the first toss, head occurs on the second toss. So if A or B occurs, or is the like the analog of union. So if A or B occurs, then we get a head on the first toss or a head on the second toss, which would mean this option of getting two tails would not be contained in the event A or B. Okay, and from a set theory standpoint, if we take the union of these two, what do we get? We are missing TT, correct?
Yes, sir.
Yes or no? So A and B are not exhaustive events. However, so let me, can I erase this?
Yes, sir.
Okay. So let me actually write down an example. So let's introduce another event. So C is the event that a tail occurs on the first toss. Now look at A and C. A is the event that a head occurs on the first toss. C is the event that a tail occurs on the first toss. Okay. So intuitively you would think that when A or C happens, okay, we get either a head on the first toss or a tail. So that would cover the entire set of outcomes, because any, we are tossing a coin twice. So this process has to start with a H or a T. Okay, there's no other options. So now to move into the set theoretic description of C, what would that mean? So C, what would C look like in terms of outcomes? A tail occurs on the first toss. So this is out, these two are in, right? So there has to be a tail on the first toss, meaning the second toss would be a H or a T. Okay. So now if you look at A union C, you get the sample space. Okay. So these four together make up the sample space. So that implies A, C are exhaustive events. Is it clear now?
Sir, yes, sir.
Okay, good. So again, just a little warning. When I first wrote down the definition of exhaustive events, what it means for two events A and B to be exhaustive, there's nothing wrong with the definition, but this A and B in the definition was not referring to this particular A and this particular B. It wasn't referring to that. Okay. So Okay, anyhow. So now the other idea, let me generate some space, okay. Let me put this up at the top. Okay, I'm just creating more room on the whiteboard. So these are our basic premises, okay? So now I wish to talk about another idea, which is the idea of mutually exclusive events. What does it mean? Mutually exclusive events. So we say that two events are mutually exclusive if they cannot occur at the same time. Okay, what would be an example? So let A be as before, event that a head occurs on the first toss. Now let's introduce another event. Let's call it event D because we have already covered C. So let A be as before and let D be the event that a tail occurs on the first toss. So the question for you is, can A and D occur at the same time?
No, sir.
They cannot, right? So in this case, we would say that A and D are mutually exclusive. So now this description of mutual exclusiveness, how did I do it? Language, plain, simple English. So now we need to describe it, in terms of set theory. We need to, like somehow be able to define this phenomenon of mutually exclusive events, because that's our whole goal, like take what we know to be intuitively true for probability and translate everything into the language of set theory. So let's see how we can do that. So to start out, let's try to describe D in terms of outcomes and the language of sets. So if a tail occurs on the first toss, that would mean the first toss would be a T, meaning the second would be a H or a T. So we are talking about TH or TT, okay? So, and we know that A is HH or HT. So what can you say about the intersection of A and D? What's A intersection D? Sorry.
0.
Null set. I mean 0, yeah, but like usually 0 is a number. In the language of sets, 0, the analog of 0 is the null set. Okay. So using the language of set theory, we would say that two events are mutually exclusive provided their intersection is the null set. Okay. So again, I wish to again emphasize that to understand each and every of these concepts, of these ideas, you need to have an example at the back of your head. That is why I'm pulling up these examples. Okay. So to understand, if I were to tell you two events A and D are mutually exclusive provided A intersection D is the null set, it really wouldn't mean much. So you need these examples to study, to truly, like understand what's going on behind these definitions. Okay, so the definition of mutually exclusive events is if two events A and D, or if we wanted, let's stick to set theoretic notation. If A subset of S, which is the same as saying A is an event, and B, which is a subset of S, be such that A intersection B is the null set, then A and B are mutually exclusive events. Okay? And likewise, this definition, just as in the case of exhaustive events, this can be extended to the case where you just don't have A and B, you can have multiple events. Okay? Multiple events. So we would say that if A1, A2, AN are subsets of the sample spaces, meaning if A1, A2, AN are events, then these events are called mutually exclusive if, and what I'm going to write is a little abstract, but let me write it, then I'll explain it. If A sub I intersection A sub j is equal to the null set for I not equal to j, where I and j ranges over 1 and n. So what's going on here? This is just a mathematically, can you see this bottom part? No, I don't think that's visible, is it? So I just wrote here, okay, this will do, this will serve our purpose. So this is just a mathematically precise way of saying that out of this collection of events, or these collection of subsets of the sample space, if I pick any two, if I consider them pairwise, I would find that the intersection is the null set. So in other words, they don't intersect. Okay, so I can pick any two, A2 and A3, and I would notice to imagine I and j stands for 2 and 3. So if I pick I to be 2 and j to be 3, then we are talking about the sets A2 and A3, and their intersection would be the null set. Okay, as long as I and j are distinct, as in 2 and 3, they're distinct, because if I pick 2 for I and 2 for j, A2 intersection A2 would be A2, it won't be the null set.
The ij
Okay.
belongs to 1 to n, right?
Yes, absolutely. That's the part I erased, because the range of values, these subscripts, AI or AJ or whatever you call it, these subscripts are basically referring to these numbers 1 through n. So, like to make this definition complete, it wasn't visible in the whiteboard when I wrote it.
Yes, yes.
I've reached the bottom limit of the whiteboard, so I erased it. But yes, you're absolutely right. So after this, you need to write where I and j ranges over 1 through n. So you could say where I equals 1, 2 up to n and j equals 1, 2 up to n. So that's how you write it. But the main part is what this is telling, like you need to understand. I mean, this is standard language of mathematics, and you need to get used to it. Again, even if you don't understand at the beginning, get used to it. So what this is telling is that if I pick any pair, okay, any two sets out of A1 through AN, and I have to make sure that they are distinct, so two different sets out of this collection of sets, and if I look at the intersection, I get the null set. Or in other words, they are non-intersecting. If that be the case, then I would say they're mutually exclusive events. And now, like maybe this is something I should have done, like before getting into the definition. How do you visualize mutually exclusive events? Okay, it's very simple. So let's say
Two Venn diagrams who are not intersecting.
I'm sorry?
Two Venn diagrams who are not intersecting.
Exactly. So let's say this is our sample space S. Okay. So that's A1, A2, A3. They are mutually exclusive. So take down these diagrams. I should have actually first introduced the diagram and then the definition. But I hope everyone is comfortable with this definition. If not, please
Yes,
ask.
sir. Yes, sir.
Okay, good.
Yes.
So A1, A2, A1, comma, A2, comma, A3, mutually exclusive. That's what the diagram looks like. Okay. Can I erase this?
Yes, sir.
And now let's talk about exhaustive sets. What do they look like? So let's say this is a set, a subset, and this is another subset. So let's say this is A1 and this is A2, and let's say this is A3. Okay. So this is what A1 looks like. That's what A2 looks like. And A3 looks like this chunk. And let's say A4 looks like this. Can you, is it visible? Oh, barely. Can you see these two figures?
So a bit is not visible.
It's just A4 and A1.
Yes,
Just
sir,
for
yes,
clarity. Okay. So A1, A2, A3, and A4. Okay. So I've just like, redrawn these figures because, it gets a little clumsy when you draw all four of them. Moral of the story is, if you look at the union of A1, A2, A3, A4, the union encompasses the entire sample spaces. Okay. So when you put these four pieces together, they're like pieces of a jigsaw puzzle. Not really jigsaw puzzle because, I'm coming to that. Forget about what I said about jigsaw puzzle. Okay. So let's say you have these four pieces. Okay. When you put them together, you would encompass the entire rectangle that represents the sample spaces. So just like, this rectangle represented S, this is also S. Okay. Now there may be overlap between the paths, which is fine. So notice A2 and A1, there's a healthy degree of overlap between the two, meaning the intersection is non-empty. That's fine, because mutual exhaustiveness, exhaustiveness has nothing to do with mutual exclusiveness. Okay. So here we would say A1, A2, A3, A4 are exhaustive. Okay, is it clear? Any questions?
Yes, sir.
Okay, now there's a class of sets that are mutually exclusive and exhaustive. So let's try to understand what those are, because it turns out when we are developing the theory of probability, these kind of sets, like they play, a significant role in the theory development. From the axioms, you might remember that, in class 11, from class 11, there were these, 3 axioms of probability, and from that, a lot of the theory was developed. Okay, so anyway, so in the theory development, these kind of, I think we can get rid of this right now. Let me just refer to my notes and make sure that, I don't have any more references to these events. Just give me a second. Yeah, we can get rid of this. So now we are going to talk about, we'll try to visualize, drawing pictures. What do mutually exclusive and exhaustive events, what do they look like? Okay, so again, let's go back to these two pictures. So for the first picture, A1, A2 and A3, as you can see, they're mutually exclusive. There's no overlap between them. However, they're not exhaustive. Why? Because there's all this space in between A1, A2 and A3. They don't cover the entire set. So these are not just mutually exclusive, you also need to bear in mind that this picture indicates that they are not exhaustive. Likewise, in the second picture, A1, A2, A3 and A4, they are exhaustive. They cover the entire rectangle. However, they are not mutually exclusive because there's overlap between them. You know, this is A1, sorry, this is A2 and this is A1. So they overlap. But for mutually exclusive sets, overlap is not permitted. Overlapping is not permitted. So you may additionally wish to note that A1, A2, A3 are mutually exclusive, but not exhaustive. Likewise, in this diagram, A1, A2, A3 and A4 are exhaustive, but not mutually exclusive. Is that point clear? Is
Yes,
that clear
sir.
to everyone? Yes? Any questions?
No, sir, I said yes.
sir.
Huh? I'm sorry, I can't hear you.
Sir,
Can
it's
you-
clear.
Okay, fantastic. So hopefully everyone converges with that belief. Okay, so we can move on. So now ask yourself, just in terms of pictures, so what would sets look like, a collection of set look like if they are to be, if that collection is to be mutually exclusive as well as exhaustive? Mutually exclusive would mean that they cannot overlap, and exhaustive would mean they need to, their union needs to be equal to S, they need to exhaust S. So if you think about it, there's only one way that can happen. Suppose this is A1 and this is A2.
The jigsaw puzzle which you were talking about.
Exactly, exactly. So I use that word jigsaw puzzle prematurely. This is the right, like context to bring up that imagery from jigsaw puzzles. Exactly. So pieces of a jigsaw puzzle are mutually exclusive and exhaustive. Okay. So this is something you need to bear in mind. Okay, because in theory development, it does play a role. I'm going to briefly touch upon that because see, I mean, the theory is great for its own sake, but in the way we do math here in India, ultimately it's the problems. You need to be exposed to a lot of problems. And today I don't think we are going to really, let's see how we are doing time wise, but we won't get into much problems. Yeah, we have we have another 15 minutes. So, let me see how far we go. But then we'll see plenty of problems, not to worry about that. But I am of the firm opinion that theory must be very clear to you before you attempt problems. Because if theory is not clear to you, and if you have to attempt problems, then the only thing you're going to, that will help you out would be memory work, a lot of memorization. Without understanding the theory, and that's not efficient. In my opinion, that's not efficient. Whereas if you really understand the theory, there's a lot of things you won't have to memorize. You will be able to derive them, I mean, very fast. You will be able to see the entire synthesis of the theory in your head. Okay. So that's how I did math, and I would recommend you do math that way. That is why, I always encourage you to ask questions if you have any. Questions are always welcome. All right, so now, so that's the picture. So that really does it for us. But then, again, since, we have these two parallel, what should I say, exposition of the theory going on. The intuitive exposition of the theory and the set theoretic formalism of the theory, formalizing it using set theory. So if we are to do that, how would we, write out a definition of mutually exclusive and exhaustive events using the language of sets? So first, let's just take two sets, okay? So A and B are mutually exclusive and exhaustive if two conditions are fulfilled. A intersection B is the empty set and A union B is the sample space. Okay. By the way, I just remembered something, and just let me know if you know about it. When two sets, when the intersection is empty, meaning there's no overlap, so such sets also referred to as disjoint sets. Are you familiar with that term?
Yes, sir.
From set theory, yeah, disjoint set. See, actually, it may be a good idea. I mean, you had set theory in 11. It might be a good idea to just kind of, like quickly brush upon set theory before you approach probability. So maybe that's what you should do. Today, I'm going to basically point out to you a few things that you ought to be looking at before you come in, for next day's lecture. But I would highly recommend that you, kind of brush up on your ideas about set theory. Okay, now, here's an idea. I don't think it's in your book, but it helps. It kind of helps. It's just a definition. So when you have a situation such as this, that you have two sets A and B, that exhaust the sample space, but their but the intersection is empty. Okay, two sets that are disjoint. When you take their union, that union is referred to as. So let me recap. Let me slowly explain again what I had in mind. If you have two sets that are disjoint, no overlap between them, and when you take their union, that union is referred to as a disjoint union of two sets. Okay, it's a very convenient terminology, not just that, more than that, concept to bear in mind. If A and B, let me rewrite this as follows. If A intersection B is empty, then A union B is called the disjoint union of A and B, and written as, this is how we often write it. Okay, you put two vertical bars and a horizontal bar below it, signifying that there's a special union going on. Okay, it highlights the fact that yes, this is a union, but A and B are actually disjoint. So we are taking two disjoint pieces and putting them together, as in these. A1 union A4 is a disjoint union. A4 union A2 is a disjoint union. Okay, there is no overlap between them. So it's just a helpful idea to know. So as in the case of mutually exclusive and exhaustive events, okay, we can extend this idea of mutually exclusive and exhaustive events in the case of a collection of sets, not just two sets A and B. Okay, so here's how the definition goes. So let A1, A2, AN be subsets of the sample space, and again, for the nth time, where n is a very high number, I would highlight that this just means that these are evens. A1 through AN are evens. Let A1 through AN be evens such that number one, A1 union A2 all the way up to AN equals the sample space, so they are exhaustive, and A sub I intersection A sub j is the empty set whenever I is not equal to j, as I and j, I comma j ranges over 1 through n. Okay, so under this circumstance, we would say then A1, A2, AN are mutually exclusive and exhaustive. Okay, Any questions on that?
No, sir.
Okay, so in this case, using this notation of disjoint sets, where is it? This notation, we could say A1 disjoint union A2, disjoint union A3, and so on and so forth, all the way up to AN is S. And the way to visualize this is this. So these are like these pieces of a jigsaw puzzle. And when you put them together, you get a disjoint union because pieces of a jigsaw puzzle, they don't overlap. Okay, so, but the union is S. When you put the pieces of a jigsaw puzzle together, you get the entire, like, picture. Okay. So that's the idea. So let me see in the little time that we have, how much more we can cover. Just a second. So now we are ready to define, all along, like, we have been defining sample space and events and so on and so forth. See, but I'll tell you something, like, I mean, today, actually, I wanted to cover way more than this, but I'm not unhappy because I would like to think we have covered the toughest part of the theory, in a sense, the most abstract part, the part that feels most unfamiliar. So what I would recommend strongly is that, number one, review your set theory. Number two, go over these concepts over and over again. Number three, watch this lecture again if you can, okay? As many times as it takes for you to really get these ideas. And when I say get these ideas, I mean, I'm really talking about this translation of our everyday intuition about probability using the formalism of set theoretic language. So this translation, you have to be very comfortable with that, okay? So now what we are going to do is, now that we have nailed what events mean, oh, there's one other extremely important definition that I forgot to mention. What does it mean when we say that an event has occurred? A certain event has occurred, okay? So let's go back to our early example. So let's say this is the sample space, okay, that consists of, tossing the 2 coins, the first example that we took up. So that's the outcome HHHT, THTT, okay? And then A was the event that we had heads first, okay? So HHHT, that's what A looks like. B is the event that we had tails first. Oh, no, actually heads last. So that would be TH and HH. Okay, so what does it mean to say that an event occurs? Now see, I mean, when you think intuitively, the idea of an event occurring, it's just obvious. I mean, you toss a coin, the event half occurs. What does it mean? Well, it just means that, I mean, sorry, you toss a coin, you get a head. Okay, so what does it mean for the event that a head occurred? What does it mean? It just means what it means. Okay, now in the language of set theory, what we are trying to do is translate everything into the language of set theory. The idea of the occurrence of an event is a little subtle. So let's study that. Okay, so given this, so this is a part that everyone understands. Let's say we toss a coin twice in a row. Okay, and let's say we observe, so we toss a coin twice. Just a second. So let's say we observe a head in the first trial. Not trial, but rather the first toss. then we would say that A has occurred, because A is precisely that event when, you know, A is the event that a head occurs on the first trial. So now we observe a head in the first toss. So let me continue with this train of thought. So when we observe a head in the first toss, it would mean that the outcome that we observe would be one of two. So outcome is either HH or HT. Everyone would agree? So far so good. Now notice that HH is an element of A, is it not so? Hello?
Yes, sir,
HH
yes.
is an element of A. And HT likewise is also an element of A.
Yes, sir.
So using the language of set theory, we would say, let me first mention it verbally, then I'll write it down. Listen to me very carefully. Using the language of set theory, we say that an event occurred, in this case the event A, provided the outcome that we get is an element of the set A. Okay? Provided the outcome that we get, either of these two outcomes, is an element of the set A. So when that happens, we say, oh, event A has happened. Okay, so A can occur in two different ways actually, which again, you know, makes sense because A is a collection of two outcomes. So let me write this down nicely. So we do an experiment. If the outcome of this experiment is contained as in like this, contained as an element. So that's what I mean by contained. If the outcome of this experiment is contained in the event, namely A, or I should here say that is contained in a given event, in a given event, say A, then we say that A has occurred. Okay? Any questions?
No, sir.
Okay, so just again get used to it. Okay, so again, you know, I mean, good thing is, bad thing is I didn't quite go as far as I wanted to, but I think the good news is that I think we have gotten some really abstract stuff out of our way. Okay, so what I would like to do is, so every class I'm going to assign a few things for you to be looking at, maybe problems to work out, and all that will happen in its, you know, own course of time. But for today's class, what I would like for you to do is first review set theory. Take notes if you know, jot it down if necessary. Review set theory that you learned in class 11, number one. Number two, these ideas, okay? Make sure that you are entirely comfortable with these ideas, okay? And if you like, you know, you can pick up your class 11 probability book and kind of, you know, make your way through it. See if some of those ideas make sense. Because the next part that we are going to get into would be certain axioms of probability and some results that follow from it. And most of the time we won't be doing abstract proof. We'll be drawing a lot of Venn diagrams though, to try and understand what is going on. Because I think that's important, like, you know, from a problem solving standpoint. So that part should go rather, you know, like, should go fast, you know, provided you are very comfortable with these ideas. Then there won't be any hiccups, you know, along the way, no obstacles along the way. Okay. Okay. So have a lovely weekend, and I shall see all of you next Saturday.
Thank you, sir.
Okay. Very welcome.
Thank you, sir.